This video is going to be about pH and pOH. In the last video, we talked about the definition of an acid and a base. And in this video, we're going to talk about acidic and basic solutions and how we can use pH and pOH to express how acidic and basic they are. So the reaction we were talking about in the last video was the autoionization of water. And we are going to revisit that here because it's important. So that reaction was 2 molecules of liquid water ionizing into an H3O plus and an OH minus. So like we did in the last video, for any reaction we can write a reaction equation for, we can write an equilibrium constant. And since this one is for water, we're going to call it Kw. The equilibrium constant is always products over reactants. And in this case, our products are H3O plus and OH minus, both aqueous. And we see that in our reactants, liquid water is the solvent. And so we don't have to include liquid water in the fraction. So it's just over 1. And this number has been experimentally determined through many, many experiments in the laboratory by analytical chemists. And it varies with temperature, as we know, but we measured this number at 25 degrees Celsius to be 1.0 times 10 to the negative 14th. And that is a number you are going to want to remember. You will need to use it later. Keep that in the back of your mind. Okay, so a couple of important things here. Number one, this is empirically determined. So that means it was determined by experiment and peer review. And another important thing to point out is this is a really small number. 1 times 10 to the negative 14th. That is 1 in a billion. And what do we know about super duper small K values? We know that it favors the reaction side. The reverse reaction is favored. So when you have a giant bucket of water, only 1 in a billion molecules are actually going to be ionizing into H3O plus and OH minus. So it doesn't happen very often, but it happens enough that we can use it to our advantage. So if we have a solution with pure water, where water is the only thing in the bucket, we know that the stoichiometric numbers of 1 and 1 mean that the amount of H3O plus and OH minus that we produce should be equal. Those concentrations are going to be equal at equilibrium. Because of stoichiometry. So if those two numbers are equal, that means that the Kw can also be written as the H3O plus concentration squared, because these two things are the same. And that equals 1 times 10 to the negative 14th. And we can solve for H3O plus by taking the square root of both sides. So the concentration for H3O plus, which is equal to the concentration of OH minus, equals 1 times 10 to the negative 7th. So that number is going to be useful. So we're going to say if we have a solution of pure water, we're going to define that as neither acidic nor basic, because water can be an acid or a base. So it's going to be neutral. So at a neutral situation, we are going to look just like water. So we're going to make a table with information about the neutral solutions. So a neutral solution will have an equal concentration the H3O plus formed by an acid and the OH minus formed by a base. Specifically, the concentration of H3O plus is going to be 1 times 10 to the negative 7th, like we just found. There's going to be one more column here that we're going to fill in a little bit later. And so now, if we think about how acids usually form H3O plus and bases usually form OH minus, we can define what an acidic and basic solution would look like in terms of these two things. So here's our reaction for water. Kw equals H3O plus times OH minus, and that Kw is a constant. So that means that these two variables are going to be inversely proportional. Inversely proportional. So if we increase one, we have to decrease the other. So if we have an acid, the acid is going to increase the amount of the H3O plus that we have in the solution. So the H3O plus term is going to be larger than the other one, larger than the OH minus. And if we have more H3O plus than OH minus, then the H3O plus is going to be larger than it is at the neutral situation. So it's going to be larger than 1 times 10 to the negative 7th. And the base is going to be the opposite. So the base is going to produce more of the hydroxide. So the hydronium concentration is going to be smaller than the hydroxide concentration. And that means that the H3O plus concentration is going to be smaller than it is at neutral situations. Okay, so we've officially defined an acidic solution as one with more than 10 to the negative 7th concentration of hydronium, and a basic solution having a hydronium concentration of less than 10 to the negative 7th. In the next video, we'll talk about how to turn these numbers into pH numbers and how to use that to express how acidic or basic something is.